So now we're going to actually do our very last module, which is counting. And towards the end, we'll talk about discrete probability, which is kind of one of the main applications of counting. So what exactly is this about? So here's what counting means. We're going to start with a description of some set, okay? And we're going to ask the question, so how many elements are in this set? And if we're lucky, the description of the set is going to be very formal, mathematical, because that'll make it easier to count. If we're not so lucky, then it's going to be vague. And so a lot of the job will be understanding exactly what the definition is so that we can write it in a mathematical form that lets us count it. Okay? So to do this, to count elements in a set, we actually have just a handful of techniques. And our job is going to be to try to apply those techniques to solve different kinds of problems. So let's talk about the techniques that we have. Now, the first one is fairly obvious, okay? Suppose that I have a whole bunch of disjoint sets. Just think of two sets, okay? And I want to know how many elements are in the union of those two sets. And assuming they're disjoint, right? And so the answer is going to be, well, that's just the number of elements in the first set plus the number of elements in the second set. So for example, let's say that we're talking about these two sets here, A, which is equal to 1, 2, 3, right? And B, which is equal to A, B, C, D, E, okay? So A has 3 elements, B has 5 elements, right? And the cardinality of A union B, the number of elements in A union B, is actually equal to the number of elements in A plus the number of elements in B, or 3 plus 5, which is 8. Okay, so the reason we can get away with this is because the elements are disjoint. Okay, so that's going to be the easiest technique we have, and whenever you see that opportunity, you take it. Okay, so for example, let's say that I walk around my house and I see 1,000 science fiction books, okay, 500 computer science books, 200 astronomy books, and 10 other books of different kinds, right? So the question is, how many books do I have? Well, I think it's reasonable to assume that all these are disjoint, right? So the answer is going to be 1,000 plus 500 plus 200 plus 10, right? And that's going to be what, 1,710? Okay, so that's the total number of books, right? That's a straightforward application of this principle. Okay, now here's a different principle, okay? And this principle has to do with Cartesian products of things, right? So let's say that I have a whole bunch of finite sets, right? All of this is with finite sets. We're not going to bring infinite sets at all into this discussion. Let's say that I have a whole bunch of finite sets, and I'd like to know what's in the cross product. What's the cardinality of the cross product? How many elements are there in the cross product? And the answer is going to be the number of elements of the first one times the number of elements of the second one, and so on, right? So let's think about this for just two sets, right? And what I want to do is I want to try to convince you that this makes perfect sense. So for example, our first set A simply has A, B, C, and B is 1, 2, 3, 4, 5, okay? So what we're going to do is we're going to think of this problem as having the A's coming down here in rows, A, B, C, and then the elements of B are going to be in the columns, 1, 2, 3, 4, and 5. So here is the kind of problem that that you might solve or you might have seen in elementary school, right? So I have 3 rows and there are 5 things in each row. So how many total elements? If you see this picture, right, this is exactly the picture that we use for multiplication. So what we have is very clearly 3 times 5 cells, right, or elements, if you will. Okay, so that's what this principle is about. That's the quote cross product, right? So it's not a big surprise that the answer is, well, multiply the number of elements in each, because that's what we meant by multiplication, right? 3 times 5 is 15, because if I add 5 to a cell 3 times, so I have 5 here plus 5 plus 5, I get 15, okay? Notice, by the way, that this principle, the multiplication principle, is actually just an extension of the addition principle, right? I have 3 sets that are disjoint. Each set has 5 elements, so the total is 5 plus 5 plus 5, or 3 times 5, 15, okay? So yeah, that's another of our ideas. And let's see how we can put this into practice. So let's say that I have 15 shirts, okay? each one of those shirts has 10 buttons. So how many buttons do I have? Well, obviously, right, I'm going to have my first shirt, right? And I have 1 button to 15 of these. I'm sorry, 10 of these, right? And then the second shirt, I'll have 10 of these. And the third shirt, there's 10 of these. And up to the 15 shirt, 10 of these. And of course, so there's 10, 15. The total number is going to be 10 times 15, or 150. Okay, so that's, again, just a straightforward application of that very same principle. Okay, now here's the third principle. It's actually slightly different than the first two, because this is the principle that's going to let us find at least these many things, or at most these many things. It won't quite tell us how many. It'll just allow us to say that that is more or less than some threshold. So it's called the pigeonhole principle. And what we have here is, suppose that I have more pigeons than I have pigeonholes, right? So for example, I might have 20 pigeons, but only 15 pigeonholes, right? And let's imagine that every pigeon flies into one of these pigeonholes, okay? Then since I have more pigeons than pigeonholes, I can now conclude, okay, that at least one of the pigeonholes has to have 2 pigeons in it. Right? Not a deep conclusion, right? It's obvious, right? You know, I mean, the first 15 can all be by themselves, you know, be very antisocial. But when the other 5 start flying in, they don't have a choice. They're going to have to go to some hole that already has a pigeon. So there it is, okay? So that's the pigeonhole principle. Here's another way of looking at it. Suppose that I have fewer pigeons than pigeonholes, and the same scenario occurs, pigeons fly into the pigeonholes, then at least one of the pigeonholes has nothing in it. Right? So again, this just lets me specify upper and lower bounds for a set. So let's apply this pigeonhole principle, right? So imagine a class as a very large class, potentially, right? And what I want to have is I want to be able to guarantee that there are 2 students who have the same birthday, okay? So how many students do I need? Well, let's assume that I have 365 days in a year. We're not going to deal with leap years, okay? So there's 365 days in a year. That means that, well, I have 365 pigeonholes, right? So each student can fly into one of the pigeonholes. So here comes the first student, and he picks this particular date, and here comes another student and picks that particular day. So those 2 pigeonholes are now full, right? And we can keep doing this. You know, and 365 students can come in, and each one of them can pick a different pigeonhole. So I still don't have 2 students sharing the same birthday. But when the 366th student comes along, he or she has no choice. He or she will have to fly to one of these pigeonholes that are already occupied. So the answer is 366, right? And that's how we use this principle.